Good afternoon, and thank you for joining us for the 20th webinar in the Offshore Wind series, Learning from the Experts. I am Leila Lashmawi, a project manager on NYSERDA's Offshore Wind team, and it is my pleasure to be joined by today's expert, Johannes Pfeifenberger with the Brattle Group. Before I introduce our speaker, a few reminders for participants and some background on this webinar series. Next slide, please. Firstly, if you're experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation for slides for all webinars in this Learning from the Expert series will be available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speaker. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or a speaker for a future webinar, you can email us at offshorewind@nyserda.ny.gov. So please note that the views and opinions expressed in this presentation are those of the speaker. Next slide, please. So it is now my pleasure to introduce Johannes Pfeifenberger. Johannes is an economist with a background in electrical engineering and over 25 years of experience in wholesale power market design, renewable energy, electricity storage, and transmission. He is also a senior fellow at Boston University's Institute of Sustainable Energy, a visiting scholar at MIT's Center for Energy and Environmental Policy Research, and serves as an advisor to research initiatives by the Lawrence Berkeley National Laboratory, Energy Analysis and Environmental Impacts Division at the U.S. Department of Energy, or the DOE, Grid Modernization Lab Consortium. So we're super excited to have you. Johannes is a friend of the show, and I'll turn it over to you, Johannes. Thank you for joining us today.
Thank you. Thank you, Leila. Let me get my slides up. Oops. It's a real pleasure joining you for this. We have a packed hour ahead with a number of topics, a little bit of background on transmission planning and why that makes offshore wind development challenging. And then we specifically go into some topics on offshore wind transmission, which is quite complex, and the industry is still in the process of figuring this all out. On transmission planning, why are we here? I think what's happening is offshore wind has made tremendous technological progress. And I like this slide by Bohm that really shows just how much technological progress there has been. The standard wind turbines that are now being installed offshore are already 12 megawatts per turbine. And, we hear people already planning to install 14 megawatt turbines. And as this chart shows, the sky may be the limit with some advanced research projects contemplating up to 50 megawatt large turbines. That, of course, requires transmission of bringing these wind turbine generated electricity to shore, and then we need to integrate it into the transmission grid that already exists onshore to supply loads. And that is really quite the challenge, because we are already talking about 30,000 megawatts of current commitments in the eastern US. There are probably going to be several thousand megawatts of floating offshore wind on top of that in the west and maybe Maine. But we see that New England, New York, and the mid-Atlantic states have already contracted for about 12,000 megawatts of wind, and they're already committed to about 30 gigawatts of wind by around 2035. But these are just the current commitments. Based on decarbonization pathway studies, we see that New England and New York alone might each require about 25,000, if not more, megawatts of offshore wind to meet the economy-wide decarbonization goals. The chart here just shows that the forecast installation of offshore wind is in fact on track to get us to about 22 to 30 gigawatts by 2030. And that's only 8 years away. So we are really ramping this up very quickly, and interconnecting all that offshore wind generation to shore and integrating into the grid is a challenge, because transmission in general is a challenging area. We do invest about $20 to $25 billion into the existing transmission grid every year. This does not include any offshore, but this is the grid that the offshore wind has to be connected to. And we don't have great transmission planning processes to make this as smooth as one would hope it could be, because most of this transmission planning is reactive in response to, reliability requirements that are being addressed sort of incrementally, one generation interconnection at a time. And this is what the grid planning process looks like. We do a lot of transmission planning for the local grid needs. This is important if you want to interconnect solar in upstate New York, for example. But then for interconnecting new generators, there's this generation interconnection process where each generator has to request interconnection, and that might be studied for several years before an interconnection is possible. So this generation interconnection process is really holding up a lot of renewable development, because it takes so long to get through that. And then there's this sort of long-term reliability planning, and what's called regional here is, region for the regional system operator. New York itself is a planning region, but other planning regions like PJM south of New York might include 13 states. And the last two boxes that we have here would be holistic planning of future needs. And that is not really happening very much. The notable exception, however, is that New York has a public policy transmission planning process, which is really working quite well, but is not fully integrated with the generation interconnection process. So how that will play out in New York is still an open question, because this coordination between the regional statewide grid planning and the generation interconnection process is really still needs to be figured out. And when it comes to the interregional planning of not just planning for New York as a region, or PJM as a region, or New England as a region, but really planning grid needs that might interconnect New England with New York, with New Jersey and Virginia and so on, that kind of interregional planning is not really happening yet in the country, not for onshore and certainly not for offshore. And there have been a number of studies, which I will show you, that suggest that this would really be necessary. This type of interregional planning is particularly challenging because of a number of barriers. I won't go through these 11 barriers which we have documented here in a survey, but everyone you talk to can immediately identify a few barriers of why this is not happening. But as you talk to people, they're not all the same barriers, and the number of barriers that need to be addressed before interregional planning and transmission development might be possible are really quite extensive. To make this all work better, we know what could be done or what should be done, and that would really be to proactively plan for all future generation needs. We know where the states are going with the clean energy standards. We know how much renewables we need to integrate into the grid. We can do the grid planning to make that possible, but we have to connect the dots and connect that kind of proactive grid planning to the generation interconnection process. Because the future is uncertain, we need to do robust planning that works across several future outcomes. But we know how to do that. It's just not currently being done, and I won't go into too much of the details there. But coming back to New York, New York is very proactive in this, and just last year published the New York Power Grid study, which really had three components: a utility study that addressed the local transmission needs within all the bubbles that you see on this chart, the sort of local, the local on-ramps for renewables, for onshore wind and solar. There was an offshore wind study that identified grid needs to get 9,000 megawatts of offshore wind integrated into the existing grid. And then there was a zero emission study, part of that broader power grid study, which really put it all together to figure out what are bulk transmission and generation needs that would get the state to a zero emissions grid by 2040. And NYSERDA has not stood still since the power grid study was done, with various subsequent studies, including some research on how to coordinate bringing all that offshore wind to shore and possibly mesh the lines that bring these wind plants to shore for a future meshed grid configuration. How challenging this all is illustrated in this chart, where you see that the share of hydro, solar, onshore wind, offshore wind, and battery storage is expanding tremendously between now and 2030 and certainly 2040. And you can see offshore wind has an important role to play here, but it's of course not the only renewable resource that the state will need to integrate. What this also shows that to make a zero emission grid work by 2040, we'll need a large amount of battery storage to deal with the intermittency of wind and solar, but also some thermal power plants that are running on renewable natural gas as a backstop for when, you know, the entire state might be in a snowstorm for a few days. Of course, the state is not an island, and it is already integrated into the existing grid, but there are significant national studies going on to explore how the grid will have to evolve further to make this all work if most of the US, so many of the states within the US, also would want to achieve a deep decarbonization of their economy and certainly the electricity grid. And some folks are talking about a macrogrid akin to the national highway system that would make it easier to diversify intermittent renewables across the entire footprint and bring low-cost resources from various parts of the US together into a more reliable, more cost-effective system. But you also see on the right here that folks are thinking about what an offshore grid might look like to really integrate the significant offshore wind resources that this country has off the East Coast into the onshore grid. How to do that is currently being studied by the National Renewable Energy Lab. The so-called Atlantic Offshore Wind Transmission Study is a 2-year study effort that has been kicked off this year. It will study what the low cost and most reliable solutions might be, both for 2030 and 2050. And you have a link here. So if you are interested in exploring the scope of this study a little bit further, this slide deck will point you that way. Many studies have found that a larger interregional transmission grid, a more robust national grid would be highly beneficial. There's almost no doubt about that. But what we are seeing in some of these studies, like this is the MIT study from last year, is that you can achieve decarbonization goals with less interregional transmission. It's just going to be more expensive. What you see here is 2 examples that were explored in this study. One is a robust interregional grid study that, as you can see, achieves by far the lowest cost on a national level. But if you don't build out the interregional transmission, as seen in this middle map here, reaching a renewable energy goal or a zero emission goal is about 20% more expensive, because you need more local resources, you need more storage, you need more backup resources, and so on. So the choice of whether we want to get to a lower cost regional and interregional grid is really ours. But as you know, building this kind of transmission infrastructure is very challenging because transmission lines face tremendous opposition. There is significant interest right now in exploring this further. The Federal Energy Regulatory Commission has a notice of proposed rulemaking coming out to improve transmission planning. And at the national level, DOE has just initiated a new national transmission planning study to explore what a stronger national transmission grid might look like and what it might take to get us there. But the challenge with all these studies, including the New York Power Grid study, is that having a study doesn't mean any transmission will actually get built. Some of these studies are a little bit aspirational, a little bit hypothetical. They're not able to establish a clear need for individual transmission lines in specific locations where the need is strong enough to support permitting of the projects. And if you don't have a strong need that you can document, it's virtually impossible to develop a transmission line. So connecting the study phase to a planning phase, to a permitting phase, is still what needs to happen, because we already know that a more robust grid would reduce the cost of decarbonizing the grid. But we do need to connect these studies to the actual planning processes and generation interconnection processes that can make things work. So now let's focus on offshore wind transmission specifically. We'll briefly talk about the type of transmission configurations that are being explored to bring offshore wind to shore, and the pros and cons of these options, with some case studies from around the world and New England, New York, and New Jersey. And then we'll talk a little bit about the mesh-ready offshore wind transmission that NYSERDA is currently exploring. Generally, what the transmission that is needed to bring offshore wind to shore is a submarine link to shore. You can see that in the yellow, that's the yellow line in this chart. You need to connect the turbine to an offshore substation and then connect the offshore substation to shore. Once you're on shore, you're probably not quite reaching the existing grid, so you need an onshore link to the existing grid. That's the orange line here. And then to link a lot of, or to inject a lot of power into the existing grid, you very likely have to upgrade the existing grid, which is the green lines here. So coordinating these three transmission construction activities can be challenging, particularly if there are a lot of upgrades to the existing grids that are needed, because that involves different transmission owners. It involves challenging onshore permitting and so on. And you can see we would have to use a whole lot of that because we have about 33 lease areas, different offshore wind development areas that would all require these kinds of connections to shore. And you can see there would be a lot of cables coming to shore if each of these lease areas would rely on several cables to bring its wind power and integrate it into the existing grid. We talked about the ISO's generation interconnection process. These are really the processes that are the only available processes for connecting new generators to the grid, whether onshore and offshore generators. But it is a very incremental process. The study process can take several years. There's a lot of cost uncertainty. You might put in an interconnection request at a certain location. The ISO studies it, and then you'll find out it would cost $500 million to upgrade the existing grid if you were to use this location. So after 2 years, you might find out that it's not cost effective to interconnect at a certain point. And that's where some planning, some regional transmission planning would really help. We'll show you some examples of how this might work, but some of this is already happening in New York. Because the New York's public policy transmission planning process right now is soliciting solutions to upgrade the export capability from Long Island to the rest of the state so that more wind could be integrated into the grid on Long Island. But to do this cost effectively would really need to require would require a study that would say, where the ISO, for example, the New York ISO would says, here's how you can integrate 10,000 megawatts most cost effectively. And, ultimately maybe the ISO New England, New York ISO, and PJM could work together on something like this. We're not quite there yet, but hopefully over the next years, we see some more coordination and some more proactive planning to really capture the synergies that this coordination would provide. So how can you do this specifically and bring offshore wind to shore? Here, for examples, the upper left shows the current approach that each wind farm has its own gen-tie to shore to connect to the onshore grid. You could modify this and say, we want to interconnect these gen-ties through a mesh offshore. So you have meshed gen-ties that would, increase the reliability with which offshore wind could be delivered to shore. Because if one of these gen-ties has an outage, you could still use the connections to the other gen-ties to bring some of that offshore wind to shore. Europe has also explored shared collector station approaches, where several wind farms would be connecting to an offshore substation, and then one very high capacity cable would bring the output from these wind farms to shore. And then there's the concept of a backbone grid, where you would have basically an offshore grid that can collect the output from several wind farms and then inject them into several locations on the onshore grid. The benefit of the mesh grid and the backbone grid is that the offshore links can actually be used to reinforce the onshore grid, because you can basically connect this part of the onshore grid to the other part of the onshore grid, say northern New Jersey to southern New Jersey, through the offshore links. But planning that kind of transmission configuration, of course, takes time and effort, and is challenging because the offshore wind generators can't necessarily wait for such a grid to be developed, and the states, including New York, want to procure offshore wind more quickly than the time it would take to fully develop such an offshore grid. In terms of pros and cons, a lot of words on this slide, but generally a planned offshore grid has significant advantages if you can use large capacity cables like 1200 to 1600 megawatt HVDC circuits, when several offshore wind plants are close to each other, so connecting them to each other offshore is fairly inexpensive. You might have to do that kind of offshore grid planning if you have very scarce right-of-way, very few landing points. New York is in a very unique situation because you have relatively little coastline compared to New England or PJM. And the best interconnection points in New York would be in the New York City area, but getting to New York City area is very challenging, as I will show you in a couple of slides. The redundancy of having a mesh grid, of course, would be an advantage, and providing a transmission solution to reduce the risk of the interconnection process, to allow offshore wind generators to connect more easily, would also create more competition, and including competition between transmission developers, because you can really do a solicitation where the most experienced and most cost-effective transmission developer would be able to build the needed offshore grid. But risk mitigation is very important, and a lot of that relates to project risk. There were some initial hiccups when this was tried in Europe, where the offshore grid that was built by a third party was delayed, so the offshore wind developer was ready but couldn't inject, and that would be a real problem if the wind developer is spending billions of dollars to develop the wind farm and the link to shore is arriving late. This kind of project and project risk is typically managed by the wind developer insisting to also build the transmission to shore, so the same party is responsible for both legs of that project, which would reduce risk. But subsequently, in Europe at least, folks have found ways to address this risk by pre-building transmission with enough lead time and providing strong performance and completion incentives that really align the interests of the transmission developer and the generation developer. Another way to get to a mesh grid, of course, would be to procure individual wind farms with individual gen ties, but do so in a way such that these gen ties could later be meshed together into an offshore grid. And NYSERDA is trying to do that, as I will explain in a couple slides. When analyzing the benefit of a planned grid, you quickly realize that with at least some planning, one can significantly lower the onshore upgrade costs by trying to figure out where to best interconnect to the existing grid. You can actually avoid a lot of very expensive onshore transmission upgrades that you wouldn't be able to avoid easily under the current approach, which just is based on one generation interconnection request at a time. We also find that by planning the offshore grid, you can use higher capacity lines and just have fewer landing points, fewer environmental impacts, fewer disturbances of the ocean floor, and just significantly reduced permitting risks and environmental impacts. Let's talk about a few real examples. This is a recent study in the UK trying to figure out how they could integrate an additional 18 to 40,000 megawatts of offshore wind by 2030 to 2040. And the map here is shown for 2030. The current approach on the left is just using, one transmission line per wind farm, and you can see there are many transmission lines that will come to shore with many onshore interconnection points. Whereas if you do a planned approach where you rely on offshore grids and higher capacity lines, you can see there are many fewer lines. And it also means by putting the lines into the right locations that might be a little bit more distant from the wind farms, but are a stronger portion of the grid, you can actually reduce costs tremendously. This UK study found that this planned solution reduces the total cost of the transmission solutions by about 19%, 20%, but it reduces the number of landing points by 50 to 70%. So it means half the landing points, half the environmental impacts, half the cable miles in the ocean floor. The UK study also found that waiting only 5 years before doing this would reduce the benefits by half. So in other words, the longer you continue with the current approach on the left, the less likely you are to realize the benefits that a planned approach on the right could provide. That, of course, gets us into a real challenging situation because we are eager to bring offshore wind online, build those wind farms, bring them to shore. And the current approach on the left is really what we know how to do now. The planning approach on the right here, we don't quite have the institutions and the processes to do this kind of planning, to pre-build these kinds of transmission solutions ahead of time and address the project-on-project risk that I've mentioned before. Taking the same concepts back to the US, this is a result from a study we did for New England. You see the wind lease areas of Martha's Vineyard here, and bringing that offshore wind to shore with the current approach of using individual gen ties and mostly alternating current gen ties. So each transmission line would only deliver up to 400 megawatts. You really see that you need a lot of cables and each of these cables would try to get to a nearby landing point on shore. And if you do that, what you see with the red lines within New England, you have major overloads of the existing grids that would require significant upgrades to the existing grid before these landing points would be feasible. If we do a plant grid using higher capacity HVDC line and planning interconnection points on the existing grid that avoid major upgrades to the existing grid, you'll see that the interconnection points are much further away. You might have to get all the way to the Boston area or to the southern Connecticut area. But what you can also see is you have fewer cables, about half the cable miles in the ocean floor, fewer landing points, fewer beach crossings, and fewer overloads and upgrades needed for the onshore grid. You spend more on the longer cables, but you spend a lot less on the onshore upgrades. And the risk of these onshore upgrades not being possible because of permitting challenges are also much smaller. This is just a map showing you where the grid, the onshore grid in New England would be overloaded if the current approach continues of bringing offshore wind to the most nearby interconnection points. We've estimated that there would be about $2.5 billion in onshore transmission upgrades. So, but beyond the cost, it's really a question of timing and the risk of these upgrades not being ready in time to interconnect the offshore grid. I mentioned earlier NYSERDA's offshore wind integration study that was part of the power grid study. That was a really visionary effort to do the kind of proactive planning that would be necessary to find feasible low-cost solutions. And the study found that if you carefully select the interconnection points by choosing the most robust and reachable points on the onshore grid, integrating 9,000 megawatts into the New York grid is feasible without major near-term bulk transmission upgrades beyond what the state has already under development. It would, however, require that 5,000 to 7,000 megawatts of that 9,000 megawatts would be routed into New York City. So only about 2,000 to 4,000 megawatts would need to connect to Long Island. That is a lower cost solution because the grid in New York City is a lot more robust than the grid on Long Island. But getting 5,000 to 7,000 megawatts into New York City is very challenging because of routing constraints. Making this all work also requires planned coordination of battery deployment, the routing and permitting, and how to develop offshore wind interconnection points in the city that actually have the space to accommodate these interconnections. You all are very much familiar with the geography in New York. You know, getting wind onto Long Island is challenging because there are a lot of environmentally sensitive areas along the shoreline. The grid in Long Island is not very strong, but getting cables into New York City has to go through the Narrows. The inner harbor is extremely constrained. There's a lot of existing infrastructure. So making this a reality does require a lot of careful planning. NYSERDA, in fact, is pursuing several of these planning efforts to facilitate how these that kind of infrastructure could be realized. This just shows again that if you plan carefully, you can have lower impacts by using higher capacity cables that go into the right locations, even if those locations are more distant from the wind lease areas. I want to briefly talk about an effort of how this could be done that New Jersey has initiated with PJM. PJM is the grid operator south of New York. As I said before, PJM covers about 13 states. Several of those states, Virginia, Delaware, Maryland, have significant offshore wind goals. And PJM is now in the midst of a process that they call the state agreement approach, where a state or a group of states can come to PJM and say, we need transmission infrastructure to meet our public policy goals. Please plan that infrastructure for us. And PJM has, in fact, initiated a state agreement approach to bring up to 7,500 megawatts of offshore wind generation on to shore, and last year has bid out that challenge and has subsequently received about 80 proposals from 13 bidders that would provide a combination of solutions, both the onshore upgrades that you see in green here, the links that are needed from the existing grid to interconnection points near the shore, the orange lines on these maps, but also the yellow lines out to the wind lease areas, and options to connect these wind lease areas through the blue lines that you see on this map. So PJM is currently evaluating these 80 proposals from 13 bidders with the New Jersey BPU. We at Brattle are supporting the BPU in this effort, and the BPU will have to select solutions later this year. They might select solutions that can bring the state to 7,500 megawatts, or they may select smaller solutions. Any kind of combinations of onshore upgrades and offshore links is possible. But it shows you that by planning it for the full scale of needed interconnections with the grid operators, you can then actually make these onshore upgrades and build the infrastructure to make this all work in the most cost-effective way. This has significant advantage over the generation interconnection process, where every wind farm would have to do this on its own, and with great uncertainty about the cost and the timing of when these onshore upgrades would be made available. Finally, I want to spend a few moments on something NYSERDA has been doing in the last year, and that is the concept of a mesh-ready offshore wind farm. The idea here is that NYSERDA might be procuring wind farms with a gen-tie to shore, but these wind farms would have a mesh-ready offshore substation. We've done some work with Siemens and Hatch to estimate that pre-building a mesh-ready offshore substation would cost about $40 million more than a traditional substation, and that's about 1% of the total cost of a large offshore wind plant. The advantage of having several mesh-ready wind farms is that if and when you want to mesh them together in the future, you could in fact do so. We've estimated that it would take about $120 to $240 million per link to build these links in the future. And NYSERDA, as you may know, currently has out a draft RFP for its 2022 offshore wind solicitation that would in fact require that each proposal utilize or provide the option to utilize HVAC technology and meet mesh-ready standards. NYSERDA has in fact put out draft technical requirements that would set out the kind of standards that each wind developer would have to meet in order to allow for its offshore substation to be meshed with others in the future. We found that doing so for New York, for example, of meshing offshore wind plants connected into Long Island with offshore wind plants connected into New York City would likely provide about $60 million in annual benefits. If the cost of creating these links would be $200 million, you can see this would be a payback of only a few years. So a fairly low cost option to procure mesh-ready offshore wind plants with the possibility to mesh them in the future. So that gets us to the end of this presentation. Just want to say that we have to keep in mind that we have 30,000 megawatts of offshore wind commitments in the eastern US already. This would require about 1,500 to 3,000 miles of offshore transmission cables, plus significant onshore reinforcements. Under the traditional approach, we would have about 75 landing points with beach crossings and about 3,000 miles of cables going to the wind farms. With a plant grid, we can reduce the cable miles by about half to about 1,500 miles, and we can probably reduce the number of landing points from 75 to probably just 25. So some proactive planning like this will be necessary to make this work. And even in places with a lot of shoreline, we may want to do that just to minimize the environmental impacts. And planning and a backbone grid is challenging. It should be done maybe for the second round of wind development in the US, but possibly a way to get there more quickly would be to rely on mesh-ready procurements, because not only would you be able to mesh together wind farms in with gen-ties to Long Island and New York City, but you might be able to mesh together a wind farm of Martha's Vineyard delivering power to Queens with a wind farm next door delivering power to Boston. And by creating a mesh grid, you would actually be able to reinforce the onshore grid by creating a new link between Boston and New York City, and between New York City and New Jersey and Virginia. We'll have to see where this takes us, but let me stop here and hand it back to Leila.
All right. Thank you, Johannes. So we have a few questions in the queue for Q&A, so we'll just dive right in. And if you need to pull up slides, you can do that again.
Okay.
So we have a question here about headroom and points of interconnection, which I think you mentioned in about the midway through your presentation. So NYSO completed some transmission studies in preparation for offshore wind back in the mid 2010s and identified 4 substations north of New York City with headroom to accept additional voltage. and the ability to expand up there. I don't know if you know what this is in reference to. Is the offshore wind program going to begin investigating those as interconnection points, or are still limited to zones J and K?
I don't know that 10-year-old NYSO study. I do know that NYSERDA's offshore wind study evaluated about at least 20, maybe more, interconnection points, and those 4 were probably part of that. The reason why the offshore wind study sponsored by NYSERDA found that you could interconnect 9,000 megawatts without major new transmission builds is because the wind farms were optimized in terms of their interconnection points. So the idea was exactly to find the interconnection points with enough headroom to interconnect the offshore wind to the existing grid. The challenge, of course, is that a lot of headroom is on the most robust part of the grid, which really is New York City, that also has a lot of load, so it could easily absorb the injected offshore wind. But getting offshore lines to these interconnection points, whether it's New York City or further up the East River or the Hudson, you still need to get through the Narrows or come in through Long Island Sound, and none of that is very easy. But I don't know about the specifics of the 4 substations that this question was about.
All right. Thank you. Well, there's another question in here. How is land availability and stakeholder concerns taken into account in the greater state-driven initiative for predetermined offshore wind connection points?
Yeah, very good question. Because interconnection points do require land. You might need to expand a substation. If you use HVDC lines, you need to have the space for a converter station. It takes land, and land in downstate New York is very scarce. I think NYSERDA is currently doing some studies looking at this. I think all the offshore wind developers, of course, are doing their own research on trying to find interconnection points. The low-hanging fruit might be to, so to speak, to recycle some of the interconnection points of existing fossil generators in the downstate area. Downstate area, I think, has about 19,000 megawatts of fossil plants, and some of them are quite sizable. So, and some of them are near to shore. So it might be possible to coordinate with these existing onshore wind generators to repurpose their facilities into an onshore wind injection point or point of interconnection. It might even be possible to use the existing fossil plant as a backup in case there's no wind. That fossil plant could in the future be converted to renewable natural gas, as the NYSERDA zero emissions study has in fact found. So that kind of coordination with stakeholders is very important. I understand that NYSERDA has reached out to other state agencies to start the process of exploring the options. But that's just about all I know about this process.
Thank you. It was pretty thorough. Realizing we do have about 5 minutes left, but there's a lot of really good questions in here, so we'll try to get to as many as we can. What is the cost differential long term of meshed ready versus a totally planned transmission? So I think this question is getting at what is the cost of just doing it all at once versus taking this incremental step? What is that step save? Is it saving or is it not?
that question has not been fully sorted out. There are pros and cons. Theoretically, having a fully planned grid can be lower cost. The challenge is that you may not have the time to fully plan and pre-build the grid before you want to get some of the wind onshore, unless you carefully plan that grid into various segments that can then be connected over time so that the build-out schedule works with the offshore wind procurement schedule. It's a real challenge. The fact that we don't know where all the wind lease areas are. For example, we might, even if we know where the federal lease areas are, New York does not know which of these lease areas would deliver to New York. So for New York to build an ocean grid to the right lease areas can be challenging if some of these lease areas would then deliver to New England because they're selected in an RFP. So fully planning out a grid has its challenges, would likely could be lower cost because it's more completely planned. To do to rely on chain ties that are mesh ready that can later be meshed together avoids some of these uncertainties, reduces the risk of not being ready in time or not building the right lines to the right locations, but may not be as efficient as a fully planned backbone grid. We might have a situation where the ideal solution is to do this next round of wind procurements with mesh-ready chain ties that later can be meshed together. And then as we look into the next round of procurements past 2030, that maybe the federal government would build an ocean grid from New England to the Carolinas and figure out how to bring the next 30 to 50 gigawatts of offshore wind to shore. And we would certainly have more time for that next round, while the first round of wind projects, maybe the first 30 gigawatts, are getting built with either chain ties or mesh-ready chain ties, or some smaller planned grid solutions.
Yeah, that you sound like you're describing a dream to me almost to have this up and down the coast just built for us. Mesh ready seems like those what we're able to do on our scope is anyways, we have a long road ahead.
We do.
A question here on the difference of HVDC and HVAC cable. Is there a reason that AC cables are not looked at the same level of HVDC? And there's another note. This can be possible by designing the right converter at the wind turbine, allowing long distance AC possible.
Good question. Long distance AC is a challenge. The good news is none of the wind areas are far enough away to make AC impossible. So it's certainly possible to have AC solutions. The challenge with AC is that as distance increases, the losses increase tremendously. So you lose much more along the way. And one AC cable right now can only handle about 400 megawatts, while a DC cable can handle 1200 megawatts or 1500 megawatts or even more. So for every DC cable, you would need about 3 to 4 AC cables, which of course has more impact. And once you get to the lease areas that are a little bit further out, you sort of get to the crossover point where HVDC actually becomes cheaper than HVAC. But one of the biggest consideration for New York specifically is you may not have the right of way to bring 9,000 megawatts to shore with just AC cables, because you would need too many AC cables, so many that you can't even physically get them into the New York harbor. And so you may want to use HVDC cables to use the ocean floor and the right-of-way more efficiently. HVDC also has the advantage that the losses over long distance transmissions are much lower. But as I said, the distance that we have to the lease areas right now is probably such that from a cost perspective, it might be about the same. Some of the nearby lease areas, it will be cheaper to use AC cables, but as I said, you need about 3 times as many cables.
Right. All right. Well, realizing we're right at 2 p.m., there's a lot of questions that we didn't get to. So if folks would like to submit questions in our inbox, we can always forward them to Johannes. And there's several comments in here regarding the mesh ready and the procurement. And I might just say that our draft offshore wind solicitation, including our mesh ready design, is up for comment. And we're happy for questions, if anything is unclear, for those to be submitted in writing. That's not related to this webinar, but just wanted to address that batch of questions. But thank you for joining us today, Johannes, and for our participants in the audience for this Learning from the Experts webinar. And to remind folks that this webinar recording and the presentation slides will be available at nyserda.ny.gov/osw-webinar-series. Our next webinar in the series is on April 20th at 1 p.m. Brandon Capasso and Donald Bullen with WRI will be speaking about weather impacts for offshore wind. So you can register for future webinars through our events page at wind.ny.gov. If you have questions for future topics that you would like to hear about in this series, please email us at offshorewind@nyserda.ny.gov. Thank you for joining us today, and we'll see you next time.
Thank you.
Bye-bye.